VP Events for Alberta AI Association. Welcome to the webinar series of Connecting Alberta AI Ecosystems with the World, organized by Alberta AI. As you might attend before and know, each lecture will take 1 hour. First, about 45 minutes speech, and then a 15 minutes question and answer session. You can ask questions in chat box, either during the presentation or after. And the speaker will answer them after the speech. So today, it's an honor to introduce our distinguished speaker for tonight's session, Bruce Matichak. Bruce Matichak gave a lecture in 2022 for us, and I'm so pleased to having this great opportunity of welcoming him back and bringing his updated academic findings. Bruce is a pioneer with a remarkable academic and professional background. He has a master's degree in computing science from the University of Alberta, MBA in health administration from Jack Welch University, and near the completion of his PhD in 2024. Bruce has established himself as a formidable force in the world of technology and healthcare. Bruce's research focuses on enhancing the intelligence of large language models for enterprise applications, and his contributions are nothing short of extraordinary. Excuse me. As the CTO for several AI startups, including Cellcorp, Point, Clinitrust, AIDANT, and MedWatch Technologies, he has left an indelible mark in the field of AI integrated systems, blood glucose detection, medical communication platforms, electronics, face recognition technologies, machine learning, and conversational AI. At HealthGauge, he spearheads projects in machine learning-driven blood pressure estimation, telehealth, and conversational agents. Recognized for his published AI research and pioneering patents, Bruce Matichak is a sought-after speaker who frequently shares his insights on AI's rapid ascent and its diverse applications in various industries. Tonight, we are privileged to have Bruce Matichak here with us, and I have no doubt that his wealth of knowledge and experience will provide invaluable insights into the realm of generative AI and its applications in health, particularly in the context of diabetes and weight loss. Please join me in giving a warm welcome to Bruce Matichak. So, Mr. Matichak, go ahead, please. Thank you.
Great. Well, thank you so much for having me. I'm super excited to be able to present some of my research and some of the things that I'm working on in the area of conversational systems, large language models. So with that, I'll begin. Ooh, hang on. So this is what we're going to do. We'll just talk a little bit about AI, conversational agents. I'm going to review semantic vectors. I'm going to do a mini course in prompt engineering. We'll take a few minutes to talk about that. I'll talk a little bit about what vector databases are, how they relate to topics, and we'll do RAG, so retrieval augmented generation. I'll just introduce that briefly, and then conclude with this, this idea of orchestration and integrating large language models into the enterprise and actually building conversational systems with guardrails, essentially. So a little bit about me. So I don't need to do this slide. You already saw that, but now you know that I played the guitar. So there we go. So that was the point of that slide. So one of the, I just recently left HealthGauge. So HealthGauge, I was the CTO and co-founder of HealthGauge, and we did blood pressure analysis. So we took a wearable and we take data off the wearable and we run AI on the data, and we're able to do non-invasive blood pressure assessment. And, we have a whole platform for managing data. Today, I'm actually working with a new company called MedWatch, and we're doing non-invasive blood glucose. So this is just some images of the device. I actually have one right here. And you put it on your your skin, and it uses AI to detect the blood glucose. And then we have a whole platform that we're building, which includes a language component. So today's topic is not about this. Today's topic is about language. That's sort of a background, what I've done. So I've done face recognition, biomedical AI. This is where I come from. So the thing about the artificial intelligence market, or let's call it the emerging language market, is it's exploding right now. And the reason that it's exploding is, there's a bunch of reasons. One is the computational capabilities of these systems have just radically increased. But secondly, the release of large language models is driving the industry at an accelerated pace. So you can see 305 billion market in 2024, rapidly growing. This is a low estimate. I've seen some other estimates that talk about an annual growth rate in the 20 or 30 or even 40% range. So it's really remarkable, and it's taking all industries by storm. So you can see this rapid rise. So that's why we're interested in this market. So this is actually showing you the market size of the generative AI share. So AI is made up of a bunch of different areas, including machine learning and optimization. These are all the different parts of AI. But the one part of AI that's really having the biggest impact right now is this generative AI. And what generative AI is, it's AI that can actually make stuff up. So if you ever seen Midjourney, or you've ever seen any of the graphics or images that are emerging, or if you use ChatGPT, what ChatGPT does that's unique is that it actually takes the AI and it makes stuff up. It generates things. And so this whole field is called generative AI. And what you can see is that an increasingly large share of the market is actually associated with that. So here's an interesting quote. If you don't know who Ray Kurzweil is, he's one of the original visionaries, if you like, for AI. And what he said is that by 2029, we're going to reach human levels. And he was saying in 2045, we'll have, multimodal, advanced artificial general intelligence. Many people are actually saying that we'll be there before that, maybe within a few years. So Ray Kurzweil, he wrote Spiritual Machine. He wrote the AI Singularity, and he talks about this point in time, that we're rapidly approaching, where it's going to be difficult to predict what happens in society because of the accelerated pace that will occur when we have machines that can just do the things that people do. So there's another interesting quote. Nick Bostrom, he's a very famous researcher in AI, and his this, I think, an interesting quote. Machine intelligence is the last invention. So, and we're already at the stage today where machines are aiding us in our inventions, and in fact, doing inventing things at a much more rapid pace than even we can as humans. So Stephen Hawking, very famous physicist, probably one of the most famous physicists ever, and he was saying, he's saying success in creating AI would be the biggest event in human history, and there's no question about that. Andrew Ng is a very famous researcher from Stanford. Did the DARPA challenge. He Coursera. He's done many things. Very famous in the AI field. And he basically compares AI to being like electricity, maybe more impactful than even electricity was when electricity transformed everything 100 years ago. This is what's happening to AI right now. So you know who Sam Altman is? Sam Altman was one of the co-founders of OpenAI, the people that built ChatGPT. And what he's saying is that we're still in the early stages and we've only scratched the surface. And I kind of agree with him. This is an interesting chart. This is the stock chart of NVIDIA. So NVIDIA is the key piece of technology that runs the AI systems for most of the world. And their stock in the last year has tripled. I have most of my stock investments are now sitting in NVIDIA because they are growing like gangbusters because of AI. So before we get into the AI, I just want to talk about some of the terms that people throw out when they talk about AI. They talk about the Turing test. So Alan Turing, very famous person who he invented the bomb. He came up with the core architecture that modern computing is based on. And when he was asked, can ultimately machines think, he wrote this paper and he came up with this thing called the Turing test. And what he basically said was, if they look like they're thinking, then they're probably thinking. So there's a couple of terms that people use. They talk about strong AI versus weak AI. So strong AI is that an AI system can think and it has a mind. I mean, it's conscious in the way that people are conscious. And what many people are saying right now about large language models, I would say many, there are many claims out there that it's conscious, that it's actually sentient, and so you can make up your own decision. Most people who are researching AI, they talk about weak AI. So AI system acts like it thinks, but and like it has a mind, but it doesn't. It's just not conscious. And this is the basis for all the commerce activity of AI, because it's in today, even in many ways, it's indistinguishable from talking to a person. And then we talk about general AI versus narrow AI. A lot of the AI that has come out up until this year, up until 2023, 2024, has been very narrow. It can only do a very small set of things. Whereas what we're seeing now is a new trend in the world where large language models are actually able to do more than just language. They're truly multimodal, and they can do language, they can do sound, they can do images, and we're very quickly approaching what Ray Kurzweil called the AI singularity, where at that point, machines are smarter than people, and we can just get them to do everything that people can do. And I think we're kind of on the verge of that. So what's the driving force of large language models? Well, the transformer network was a major innovation that occurred. It's deep, it's huge, and it has emergent intelligence, which I will talk about in a second. It's also multimodal. It can do text, it can do images, it can do voice. It has some limitations when it comes to complex reasoning, but what we've seen is that large language models can do many of the things that humans can do. It can pass the bar exam. So basically a lawyer, it can be a lawyer. It can pass a medical exam. So it can be a doctor. It can teach, it can automate, it can do all of these different things, and it can do them really well. Now, what we've seen is that in certain contexts, it fails. So I'll talk about that a little bit later, what kinds of failures and how do we build systems that make use of that intelligence, but still allow us to do work that we want done. So this is the DNA, the transformer system. If it was the major invention of Google when they wrote their paper, attention is all that you need. And then ultimately, OpenAI came up with the transformer system. They released that in the form of ChatGPT. And this is more or less what the network looks like. So it takes in input in the form of words. It divides those words, it figures out where the words go, and then it goes through layers of artificial neural nets, which are these structures in AI that take information, process the information intelligently, and then come up with an answer. And it's autoaggressive. What it does is it analyzes the entire sentence. It figures out what the next word is, It then analyzes that whole new sentence, figures out what the next word is, and it keeps going word by word until it can make up an entire document or a novel or a song or something or whatever you want it to do. It's called generative AI because it's actually using AI to generate things. So this is a little bit about the history. So GPT-1 came out 2018, very quickly followed by 2, 3, 4, and 3.5 was basically a watershed moment or event because they combined transformers with what's called reinforcement learning. Reinforcement learning, University of Alberta, we're probably the foremost university in the world developing reinforcement learning, although it's being developed all around the world in various institutes. But it's a way to it basically they use it to train ChatGPT to respond in a more human-like manner. And so once they combined reinforcement learning with the transformer model, it really took off and spawned the whole large language model industry. So it's smarter than most people, language expert, it can do knowledge synthesis and much more. What's really interesting about large language models is that their vast improvements occurred while they made the system bigger. So a lot of the improvements didn't come because they re-engineered the system over and over again. It just got smarter and smarter and smarter the more parameters or the bigger of the model that they made. And so, and what happened was as they build large language models ended up with this emergent behavior. So these are behaviors that were never trained into the system. So language translation, for example, was never trained into the system, and yet it does language translation. Solving math problems was never trained. Transliteration never trained. Word unscrambled. So all of these problems, they weren't trained in the system, but they emerged as capabilities once the model became big enough. And so it's almost like Ghost in the Machine, right? If you ever watched iRobot, very famous scene where he talks about, the ghost in the machine. It just starts doing stuff and nobody programmed it to do it. And in fact, large language models are still largely a mystery. Nobody really fully understands why they are so smart and why they do the things that they do. We just know empirically when we put our input in, we get these super intelligent behaviors back out. So the whole industry has spawned many different large language models well beyond ChatGPT. So GPT-3 came out, ChatGPT 3.5, GPT-4, but we've also seen Llama from Meta, so the Facebook people, right? And what happened with Llama is that ultimately the parameters for the Llama model got open sourced, and now there are many large language model versions of Llama that you can run on your own computer. In fact, I just was playing around with Ollama. So if you want to try running a large language model on your own computer, you go to ollama.ai and it will let you download your own ChatGPT, and it's almost as good as ChatGPT, and you can run it on your own computer. So Llama, Alpaca, Claude is amazing. I think Claude might actually even be smarter than ChatGPT. So I've asked Claude questions about financial analysis, and it does a better job than ChatGPT does. Falcon's out of Dubai. They invested billions of dollars and they came out with it, and it's really quite good. Cohere, this is our Canadian group. So these are guys that actually came from Google Brain. And these guys were some of them were the authors of the Attention is All You Need paper that kicked off the whole thing. And they created a company, and Cohere now is worth hundreds of millions of dollars, and they have a very good tool. Grok, if you don't know who Elon Musk is, Elon Musk, the guy who has um, SpaceX and Tesla and whatever. He started a company called Grok. So he was originally one of the guys who started OpenAI, but then he didn't like the direction of OpenAI. He left OpenAI and he created his own thing called Grok. And Grok is supposedly better than ChatGPT. I mean, some people say that. And what they've done is they've open sourced the whole thing. So on March 17th, they open sourced Grok. And so these are models that you can get and run in the enterprise or run on your own computer, even in some cases for the smaller models. So let's dig into large language models, what's actually inside of them. So we did that. Let's go. Well, so they're based on these large language models are based on this transformer, and they're based on this idea of the semantic vector. So I'm going to explain a little bit about semantic vectors next, because you're going to need to understand those ideas to understand how vector databases work. So let's just talk about semantic vectors. It's a core concept in language models, and it's critical for vectorizing your language statements. So why vectors? Because what you want to be able to do is take a conversation, take an entire phrase, and you want to be able to convert that phrase into a set of predefined values that you can store in a database, so that you can later on go and when somebody says something, you can find the most closest semantic match to what they're saying without having to do all of this parsing or processing or keyword search matching. And so this is what these vector databases give us. And so what ChatGPT does, and what all the LLMs do, is they give you the ability to take any phrase, vectorize it, which means turn it into a vector, a set of numbers that you can then store and retrieve. So it's vector storage is specialized storage. It's designed for high dimensional vector data that you can rapidly retrieve. It has dynamic data handling. So Pinecone is probably the #1 vector storage company out there. And the advantage of vector storage is that you get answers instantaneously once you're in vector storage, and it's very, very, very cheap. And so this is a key part of building orchestrated systems. So let me talk a little bit about where these vectors come from and what they mean. So whenever you take a word and you run it through a large language model, it tokenizes your phrases. It divides up your input into individual words, and it basically assigns a vector, a set of numbers that you can think of as positioning that word in semantic space. So if you think about space as like this big, 3D open space, and some position inside of that space is where the word is. Well, things that are similar are located in similar locations in semantic space, and things that are dissimilar are located far apart in semantic space. So if you want to find if two ideas are similar, you just can take their dot product. You take their dot product and you instantly know, hey, are these concepts similar? And that is the basis for large language models working. And in fact, this concept is easily demonstrated by taking a word embedding, and you take the semantic vector for king, you subtract the semantic vector for man, you add the semantic vector for woman, and guess what you get? You get in semantic space this, the location for the semantic vector queen. So semantic vectors, again, are key. And so here's a way to explain if I'm comparing two semantic vectors. I'll give you, I'll illustrate this with an example. Let's just say that you had a whole library of movies that you might want to watch, and you take the attributes of a movie. So does it have romance? Does it have action? Does it have comedy? And you take every single movie in the entire database and you list off those attributes. Now what you want to do is you want to find, hey, which movies would I like? You don't want to go through each movie and do this step-by-step comparison. What you can do is if you take your particular attributes, I like comedy, I like action, you line them up so that all of these attributes line up exactly, you can instantaneously go through and compare all of those words and all of those movies and find instantaneously the movies that you care about. This is the mechanism of large language models. What it does is it takes the entire string and it takes every single word and it compares every single word to every other word and it figures out how do these words go together? And it does this in layers. So this whole thing here, this box here is a layer. And in ChatGPT, there's 100 of these layers. And these sentences can be thousands of tokens long. In fact, one of the original limitations was you can have like 1,000-word sentences in ChatGPT in the original ChatGPT, but modern large language models can actually handle hundreds of thousands of words. So literally you can take an entire book and send it to the ChatGPT. It'll process and it'll compare every word to every other word and it'll come up with analysis. And then that analysis will do the same thing with that analysis through many, many, many layers, and it'll come up with the best next word so that you can then use this to generate anything you want. So this is the idea of the ChatGPT architecture. So when we're actually building large language models, what we have to do is we have to engineer. What we're doing with prompt engineering is we are creating concepts that the large language model can use to do intelligent generation, because these prompts tap into patterns of thought inside of the large language models. So if you describe your problem in a mathematical way, it'll access mathematical thoughts. If you describe your problem in a pedagogical way, it'll access, thoughts of training and teaching, and it'll be a good teacher. So how do we use this idea? Because what we want to do is we want to ask the language model questions and we want it to give us smart answers. The key is knowing how to structure your thinking so that you elicit thoughts from the large language model in the form that you want. So we craft instructions to elicit specific responses. And effective prompts, what they do is they provide the context. In fact, you can think of it like if I'm talking to a person, how would I instruct a person to do something? The more specific you can make your instructions, the more intelligent that model is going to be. So this is more or less how it works. You got a task description, you give it some input, you indicate here, start your output from this point, and then it'll do this auto-generative completion of your prompt. So this is an article followed by a summary written in informal language. And then your input would be the article, whatever that article is. And then you say in summary, and it'll just, boom, it'll spit out it'll spit out a summary. In fact, in modern language models, like you don't even have to say in summary. It'll just know when you put your input in there, it'll just know that it has to do some output. But it can be wrong. So here's a really interesting example. It's very sensitive to the way that you word your question. So if I say, if X and Y are the tens digit and the units digit respectively of the product, so the tens digit is like here, and the units digit is like here. And if you add the tens digit and the units digit respectively, so first of all, you have to multiply these things together and then add those together. And so then so here's my calculation of that thing. So 4 and 8 should be 12, but it comes out with the wrong answer, right? So But if you just change it a little bit, all I do is I say, I need you to solve a math problem. That's all I did, is just add that context to the prompt, and lo and behold, it gets the answer right. So yeah, so there you go. You can see the correct answer down there, right? So the large language model is very sensitive to the way that you phrase your question, the context and the things that you give it. The more you give it to think about, the smarter it gets, right? So try this thing. How many duplicate letters are in the number 19? If you put this into Chat GPT-4, it will it may or may not get it right? So sometimes it gets it right and sometimes it gets it wrong, which is kind of also interesting. So this is one of the things that you can do to increase the accuracy of your prompts is do this thing called reverse prompt engineering, where what you do is you just ask ChatGPT, hey, here's kind of what I want to do. Can you create a prompt for me? It'll end up giving you this prompt. You then prompt it with the prompt that it gives you, and you end up with better results. So this is idea of reverse prompt engineering. So prompts can have a lot of structure to them. So you can you can put your sentence in there, you can go question, so have this input indicator, you can have an output indicator. So you can put a whole bunch of structure into your prompting, and the prompt will actually emulate that structure and come up with answers for you, matching the structure that you actually give it. So prompting with examples is really critical, and here's why. And that's because when the language model is trained, this was an emergent behavior. No one trained it to do this. It just did this. So zero-shot learning, there's tons of things that it can do that it just knows how to do if you just give it the ideas. For instance, language translation. You just give it your language and you say, here's a bunch of thoughts. Can you translate them? And it just knows how to do it without any additional examples. There's this thing called one-shot learning, and it's not really learning in the sense that it's, like a machine learning thing. It's basically just learning in context. It learns how to respond in the way that you want it to respond. And if you give it just one example, it will do a much, much better example. And then there's also this idea of few-shot learning, where you give it a bunch of examples that are very similar, and it will be very intelligently come back with answers. So I wrote this paper that got published in Medium, where this is early days before it could do database translation. I trained it to translate natural language sentences into SQL just by giving it a bunch of SQL examples. And so this is kind of a very, an important concept in prompting is giving it examples. And you can make your examples structured. So you can have a sentence and then a review, and you can have multiple parts. You give it a few examples of this structured output, and it will follow the structure that you give it. So the key points of engineering are that if you give it detailed instructions, it ends up producing better results. You can do few-shot learning. Prompt combinations can be used as well. All right, so this kind of gets into the area of research where I'm doing a lot of research. So what I'm working on is, how do we make conversations intelligent? And so in order to do natural language processing, you have to give it the skills of natural language processing. And what you want to do is use the large language model to process language, but not necessarily to process the entire workflow. There are systems out there, so AutoGen and Crew AI, and what are some of the others? There's a bunch of systems out there that actually try to get the entire process out of the large language model, convert that process into some code, and then if it breaks, go back to the engine and ask for changes. And this whole mechanism seems to work fairly well for simple problems. But if you're trying to build an enterprise system, what you want to do is do all the workflow yourself. And what you're going to use is you're going to use the engine, you're going to use the chat engine, the large language model engine, to translate the goals of the person into a series of workflow steps that you then execute. And so let's talk a little bit about how we do that. So it turns out that dialoguing is like this node system. So again, this is the area of this is my PhD research. We can convert dialogues into these graphs, and we can use planners to actually execute series of steps throughout the conversation, so that the conversation itself can be planned out in advance, and the agent can guide the user through a predefined set of workflow steps. So this is an example of trip planning and just a conversational dialogue that you can draw up. And again, this is automated by a planner. So the beauty of this technique is that it's got guardrails. The agent knows about its knowledge limits, and then it can get help from, if it requires it, because it can go through the workflow and get that help. And we can make the behavior goal directed, which means that it can plan out a set of activities that are, it can run a plan of a set of activities. All right, so conversation goals. So these conversation goals can recognize the topical focus. They can progress through these conversational states. They can interpret the state of the conversation. And so they can recognize, okay, this person doesn't know about this thing. Well, in order for me to be able to explain this, I have to explain these other three things. And so again, in goal-directed conversational systems, these are the kinds of things that we can implement in systems. So again, this is the area of research that I'm working on. So okay, so this next part gets into building a conversational agent today with planning systems. So the first thing that we do when we implement these systems is we vectorize the input using that embedding vector that I talked about. And we go to a vector database, we figure out what the topics are. Once we figure out what the topic is, then we can ask the orchestrator can then orchestrate a series of activities. And let me talk about how the vectorization process works. And then I'll show you how the orchestration works. So this is how vector database work. In advance, you have a whole bunch of topics or documents, or could be images or audio, or things that you want your agent to know about. You run them through this vectorization process. And in the case of large language models, the large language models can vectorize anything. They can vectorize a word, they can vectorize a sentence, they can vectorize an entire document, and they can store that vector in a vector database. And then at runtime, when you go to do a query, all you need to do is take your query, run that through the large language model, get a vector, and then go to the vector database and instantaneously get your results, which could be, hey, run this workflow, or hey, do this other task over here. And this is how vector databases are used with large language models. So when you're actually using large language models, a bunch of your data is not coming from the knowledge of the system. Large language models know a lot, but they don't know everything. They don't know everything about your data. They don't know everything about your company. They don't know the transactions that your company will run. They don't know about your files. They don't know about, there's lots of things they don't know about. And what you need in a system that you would deploy in the enterprise is you need something that can translate the queries that you make to the large language model into queries that will go to your internal database systems. And this is what we do with orchestration. We use the large language model to tell us how to talk to our databases, and the orchestrator then talks to the database for us. So this is closely associated with retrieval augmented generation. So I'll talk about that in a second. So with retrieval augmented generation, what you have is you have a bunch of things that you want to be able to, a bunch of ways in which you want to get the engine to respond. And so you have prompts that are ready to go, basically. You have a whole bunch of prompts that are ready to go to drive a bunch of different activities. So what you do is you take the user's input and you go to the vector database and you figure out from the user's query which prompt to use. And so we augment the retrieval and we augment the generation by retrieving the correct prompt for the context in which we're in. And so this is just an explanation of how that works. All right, so I'm going to finish up here with talking about orchestration. And so this is my system. So this is the system that I'm building, and I'll just talk a little bit of what these pieces are. So the first thing that you have at the very top left is you take all of your textual data. So these are your documents, or these are the things that you want to say, or these could be topics, and you run them through this embedding model at the top here, and you vectorize everything and you store it into a vector database. Some of those queries might actually go into this graph database system. So another way to organize knowledge is using graph databases. So vector databases, graph databases. This allows us to essentially pre-configure the kinds of queries that we want to be able to make to the system. So at runtime, a query over here, I don't know if you can see my cursor, but the query goes into the host. So the host could be like a chat system, or it could be a web page, or it could be, whatever you're using to actually interface with the large language model. And the query will then get transmitted to the orchestrator. And then the orchestrator will take that query and go, okay, it will then run the embedding to get the embedding version of the statement. It'll go to the vector database, it'll figure out what the topic is, and then it'll decide what it wants to do. So one thing that it might do is it might go to a database and get some database query, and it'll bring that back into the orchestrator. Another thing it might do is it might do something called thought extraction, which is basically asking the system to plan out and execute a series of steps. So you go to ChatGPT, for example, and you could say, how do I solve the problem? What are the steps to solve this problem? What the orchestrator can do is then take those steps, and then it can actually execute those steps one at a time. So that's what an orchestrator do. In some contexts, you want it to do symbolic processing. For example, you might want it to do math, right? And large language models are not very good at math. Like, they're hilariously bad at math. And so what the orchestrator can do is it can go, oh, I realize this is a math problem. It can go to the symbolic processor, and it can just get the symbolic processor to answer the math question. And then once the orchestrator does that, it can put it all together, and then it can again go to the large language model and format the input in a way that the user wants it. So some other things that it can do is it can do constraint process. All right. We got noise on the line. All right. So I'm basically done with my
Excuse me,
query.
can you, Wenjie, can you please turn off your microphone, please? Thank you. Okay.
All right. So that's the end of my talk. So so questions.
Okay. Yeah. Hold on. Okay. Thank you very much, Bruce. I like your presentation. It's very clear. And I think the large language model you explained very, easy understanding. I'm not sure if the audience here, you understand a little bit, because I know most of you might not have a, background of AI. But yes, we have already recorded this webinar. So if you like, or if you are interested in, you can go back to review today's webinars to learn. So, so are there any questions from the audience? It's a great opportunity to ask questions about AI. Especially the Bruce talks a lot about ChatGPT. I think everybody knows about ChatGPT and already get a lots of information what ChatGPT can do. And everybody, I believe you use the ChatGPT to help your daily questions or any other interesting things. So any questions? Okay, so waiting for the audience questions, I'd like to ask a few questions, Bruce. Is that okay?
Great. That'd be excellent.
Okay. Yeah, I like your presentation. Also, I think your PhD research topic is also interesting. I wish you good luck to get some findings. Since I just want to ask some generic questions so that the audience can understand. So there's an interesting question that, Elon Musk, he asks OpenAI to open source their code. Do you agree or not? Yeah, just have fun to answer this question. What's your points?
Well, so he did. I mean, he open sourced Grok, as you saw, in March 17th, 2024. So that was very recently. But if you open source it, how do you make money, right? So and there are a bunch of companies that have created open source large systems, generative AI systems, and a bunch of them are struggling, right? So I understand the objective of having a commercial product. Now, I think they should open source some things, but I don't see the need for open source, putting everything out on open source. Now, the argument that people have, and this was the original argument that started OpenAI in the first place, was that there's a few companies that are gaining all of the benefit of AI, right? So you can, small number of countable companies that are achieving most of the revenue associated with AI, with large scale AI products. So Google, Microsoft, Amazon, like all the major tech companies are gaining disproportionately more value than your small average guy, right? And so the whole motivation was, hey, this should be shared. All of this research came from publicly funded research in the first place. It's not fair to have the small group of people take all of the advantage of it, right? So that was the original motivation. But practically speaking, if you're going to release a commercial project, you need money to support it.
Mhm.
And so I don't see how you can have a company where all your it's not there's not that many business models that work with the open source business model.
Mhm. Okay. Yeah, from my point of view, I think because the AI, we have to, make it in control. We don't know if they do open source code. We don't know
Hmm.
what is embedded in their
Hmm.
products, so that
Hmm.
might goes to some unpredictable direction. Yeah.
Well, it here's the thing is like the code for OpenAI is tiny. It can be written on a page. There's not much code that actually runs the large language model. It's a small amount of code. And you can use OpenAI to write OpenAI. You can actually ask it and it will write the code for itself. The most
Mhm.
of the magic is and capabilities is frankly in the training. And so we train and train. And so if you look at the models that have come out since then, these models are are massive, but they're very intelligent and they're just as intelligent as ChatGPT. And they got their intelligence through training, right? That's where they got it from. So, but that's where a lot of the expenses. So training these things actually costs millions, tens of hundreds of millions of dollars. I mean, I think probably the first like ChatGPT 3.5 was in the tens of millions of dollars to train. And then they keep retraining it. So they're constantly investing in fine tuning and retraining and fine tuning and retraining. And so
Yeah.
I don't expect them to open source that, right? But the code, I mean, the code is not that magical. Like you can write the code yourself.
Yeah, that's a good point. Yes. Yeah. Okay. So, have you aware of? I'm not sure in your area, because in my research area, I already found that a bunch of research training is becoming to use artificial intelligence methods instead of uh, using traditional dynamic models, professional
Mhm.
models to
Mhm.
study. So and some
Yeah.
of time that the results and outcomes using the AI is better than we use the traditional research methods. So how do you think?
Mhm.
What's your point on this trend?
Well, if I can interpret what you're saying a little bit, do you mean AI to generate data? Do you mean using AI to generate experimental
It's just
procedures?
using AI by taking advantage of lots and lots of sufficient data,
Mm-hmm.
so that some hypothesis research can
Mm-hmm.
get the better outcomes than
Mm-hmm.
traditional research, like we use some professional dynamic model or professional physical models that
Mm-hmm.
sometimes doesn't work better than AI. So is there
Yeah.
a clear trend?
Yeah. Yeah. So how do we use AI? I think that's really the question. And what is AI? What do we mean by AI? What we mean by AI is basically getting the machine to think. That's what we mean by AI. So what can we get it to think about? So it can think about problems and solve them, right? Should we get it to think about problems? Yeah, we should get it to. The problem is being able to take your problem and putting it into a form that some AI algorithm can work with, So for example, like machine learning is a branch of AI, and one way to build machine learning models is to handcraft them yourself. But the other way to do it is to give an AI the problem and let it handcraft a machine learning model for you, right? And so, in fact, and these things are very good. So So AutoML and other kinds of machine, AI systems are designed specifically to help us make better models. So certainly that's happening too. Here's some other things that we're doing with generative models. So generative AI is large language models fit into this class of generative AI systems. And what they do is they use, these statistical techniques to be able to spit out extremely sophisticated things. In fact, entire articles or books. Researchers have even published papers that have been generated by these generative models. The question is, are they right? Are they, is the reasoning sound in an LLM? And in fact, it's not, right? It reaches limitations and it breaks. And so what I think is the solution and where things are going to head for all areas, both commercially and in various research fields, is a combination. And so this is why, if you look at my orchestration model, what we want to use AI for, and generative AI, is to take our language statements and to convert them into some symbolic representation that we can then hand off to an automated reasoner in some particular area, right? So, so if you want to, I want to schedule for all the nurses in the hospital. Well, the way that you used to do that is you used to, spend all this time to build a constraint model so that you can then, schedule all the nurses in the hospital. Well, with a LLM based system, it can just write the constraint program for you and then run that constraint program on a constraint system, right? So this is the use of AI. Is it's kind of like we're using generative AI to help us actually implement traditional models and run those models on traditional solvers. So I don't know if that answers your question exactly, but that's kind of where I see this whole industry heading.
Yeah, I agree. You said, okay, the combination of AI and the traditional, so that works better. Yeah, but I do see, the trends, the people, the researcher, they turns to the direction that, using AI, taking advantage of those data, because yeah, sometimes the relations between why that data shows up is hard to explain using the traditional model. But if we just feed the data to the AI algorithms, then yeah, something magic things happen.
Yeah. Yeah, so that's a problem, right? There's some magic that happens, and it's all black box. It's not. So there's this whole field now emerging called explainable AI, right? Where, like if you're in a legal case and you can't just ask the AI, is this person guilty? Yeah, guilty, like what you needed to do is you needed to explain all of its reasoning steps. And here's the problem with large language models is it's impossible, because the number of steps that went into solving that problem, say, is this person guilty, there's billions and billions of tiny little transactions implemented by all of these neurons, and it's impossible to sort it out. You can only sort it out in sort of the aggregate form, right? And this is why I think that here's one thing that we can do with all of that knowledge. The fact is that we know that it thinks, and we know that it's smart, and we know that it can solve these problems. We just don't know what the model is that it's using to actually solve those problems. So what we can do is try to get its knowledge to be more explicit. So what we can do is ask it, well, what do you think the model should be? And in fact, it can generate these models that are executable. And so this is where, a bunch of the work that I'm doing is trying to basically mine the large language model for knowledge and information that we can then extract into an explicit, explainable form. So, because if I can show you, oh, here's the decision-making model, and that decision-making model, it's all explicit. If it lines up with the decision that the large language model makes, then I think we're okay. And that's where we have to go with legal systems. That's where we have to go with doctor systems even, if the model says, yeah, you need to amputate, well, I'd like a little backup, before I start the amputation process, right? Give me your reasoning, right? Tell me explicitly how you got to that conclusion. And this is only possible by taking the reasoning out of this massive, it's like a big ball of goo, right? This whole mass of weights. And you have some, and you don't know what exactly is the decision-making process.
Yes, exactly. Yeah, thank you for discussion. So we have one question coming from the audience. Let's finish by answering these questions. Okay. So before I ask the question, I just wanna let the audience know. Yeah, there's a video recording. As you can see in chat box, we recorded today's webinar. You can please look at the chat box. There's a link Li Han sending to everyone. So the question is that, can you compare the embeddings and the fine tuning when used to customize language models? Thanks.
The fine tuning, sorry, what? Yeah.
Yeah, the questions in chat box compare the embeddings and the fine tuning.
Well, embedding is a different thing. Embedding using the okay. With embedding, what we do is we take the large language model and we use it to generate a semantic vector that we can then compare to other statements of the same kind, right? So you can use an embedding model to say, like let's say you have a catalog of a million products, right? And each product is described in a particular way, right? You got a description, you got a million descriptions. And then a user is typing and they're searching through the catalog and like, I want, coconut tasting milk, so they just write this phrase out. The thing is, no description in that entire database is going to exactly match your query. So what people used to do is they used to do keyword matching, right? So they'd look at, oh, there's coconut and then there's milk, and then they would count the words and they would find the queries that have the closest word counts. And it's terrible. If you try to search a catalog of a million things using keyword search, it's terrible. It just doesn't work at all because you have to use exactly the right words that match the thing that's been described. Whereas embeddings convert your statement into semantics and generate a semantic vector that represents the idea of what it is that you're querying for. And then instantaneously, you can search the vector database for whatever it is that you were querying for instantaneously. You could have a million things and you would find the thing you're looking for instantaneously. So there's another way to make models smart about things like catalogs, is you could fine tune it with all of your catalog data. So you take your model and you say, okay, well, I'm going to train the large language model I'm going to give it these descriptions of all these things, and I'm going to give it this description, and if it comes up with this description, I'm going to match it to this token, and if this description token, you could do token matching or phrase matching or various ways. And so then when I type in this query into the large language model, the large language model will be able to use its fine-tuned understanding of my language to be able to do the catalog matching. It's probably not a very good way to do it. Probably won't work that well. It's probably really, really hard to separate all of these products using fine tuning. Fine tuning works really, really well in cases where you have in your business or in your work context, you have a particular way that you word things, and it's different, and it's a different way of wording things than, the rest of the world or the rest of language. You can then fine tune the model to use words in the way that you want them to be used. That's where fine tuning works really well. It does work in the context of, matching specific queries, but the embedding technique is way, way, way better for catalog matching or topic matching. Whenever you have a big list of things, you're way better off to use the embedding technique rather than the fine tuning technique.
Okay, yeah, thank you for answering. I hope it answers the audience question. So there's a new message. Okay, thank you. All right, okay, thank you everyone for attending tonight's webinars. Thank you so much, Bruce. You're bringing us a very clear presentation. I really like it. So if you are interested in tonight's webinars, you can visit the YouTube channel of Alberta AI. Yeah, we have already delivered it on a YouTube channel, and then you can also, transit to your friends if they are interested in. Okay.
I'm sorry. Can I have a question? One last question.
Sure.
Okay. Yeah. Ask
I have
quickly.
time.
Okay, thank you.
Go for
Okay,
it.
so I just wonder the data we use to train AI, how do we know it's unbiased? Like where do we get the data to train the AI? Like,
Yeah.
well, thanks.
Is your question, where did OpenAI get its data? So originally it got it from Wikipedia, Library of Congress, all of the, major works of literature that were, and it was largely, and it was biased. It's like, it's North American, Western information. So that's where a lot of its knowledge came from at first. But increasingly, as that, as people use it and as they train it, they get more and more data in. So each successive generation is better than the last, but there's lots of bias. There's lots of in there, and that's one of the major areas of research is how do we balance the input so that it has a more general wide-ranging understanding of all of the ideas of mankind, not just this narrow set of ideas. But yeah, that's a problem. So where does its data come from? Whatever the trainers put in. So what some of these other large language models are doing is they're fine tuning it or training it on other kinds of knowledge, and you can imagine that could be a good thing, but it also could be a bad thing, because you could very easily train a large language model to be bad just by giving it lots of bad ideas, and I'm sure people are trying to do that. But yeah, its input comes from whatever the research put in.
Yeah, I think the expertise, the knowledge is also required. Yeah.
Thank you for your thanks for answering my question. A follow-up question. Individually, how do I make sure I'm represented in the data, like the use in the AI? Because as I learned from you, the AI is now becoming applicable to a lot of fields in our everyday life. So how do I make sure I am represented in that?
Well, I mean, as an individual, you can't. I mean, there's billions of words that have gone into training. So your entire life story might not. It's like a drop in the bucket, right? Relative to all of the other people out there. So So you can't be represented directly in OpenAI. Although what you could do is you can go up in OpenAI and you can create a fine-tuning model. And then what you can do is you can give it your life story and put your life story into the fine-tuning model. And then you'll get a version of OpenAI that you can run that has all of OpenAI plus your life story. And now you can talk to that. And, and so that you can be assured that that's going to have your perspective, and in fact, you could create your own agent off of that and give it out to your friends, right? But there's no way that OpenAI directly is going to be able to represent your story.
Thank you very much.
Okay. Yeah. So we don't have time. I think that Bruce need a thank you very much. And you still have a presentation tomorrow night, right, Bruce?
Yes, yeah. So there's another one. I can send you the information for it. It's on LinkedIn.
Okay.
I can put it. I will post. I've posted it, but I'll post it as well on my page, and then people can go to it. But it's going to have a bunch of the similar elements to what we're talking about here today, but it's also short. I think they're giving me like 20 minutes or something, so it'll be
Okay.
compressed. But yes, thanks for bringing that up.
Yeah, I tend to attend your webinar or in person.
Oh, okay.
Okay, yeah. So so you will post it or you send it to me. I want to attend it.
Okay. I will post it or send it or both.
Okay, okay. So thank you everyone for attending tonight, and good evening, and let's say goodbye.
All right.
Oh,
Thank you. That was fun.
thank you, Bruce. And I'm
Thank
looking
you.
forward, yeah, looking forward to bringing us the next, your topic is
Okay,
interesting.
good.
I still think you have so much content that doesn't have time to present, but I like to,
Yeah. Yeah, I could
Yeah.
do one on actually using my system to build an agent if you want to do that.
Mhm.
I could do that, and then people can use it and then give me some ideas about it. That would be useful.
Wow, awesome. Yeah, so AI agent is also a big, stream, right, for
Yeah,
AI research.
yeah, absolutely.
Mhm.
All right.
Okay. Yeah. Thank you, Bruce. Yeah. Thank you, Bruce, for your presentation. Yeah.
Oh yeah. Hi, how you doing? Good to see you again.
Yeah. Yeah. I'm good. Yeah.
Okay.
I'm moving to Silicon Valley. So when you visit the Silicon
What?
Valley, let me know. Yeah.
Oh, okay. Well, good. Well, I'll come visit you. That would be good. That'll be great.
Okay. That's good. Okay. Okay.
Okay,
Okay.
great.
Okay.
Yeah, good evening.
Okay.
Have a
See
good
you
night.
next time. Yeah. Bruce. Yeah. Bye
Okay,
bye.
thanks
Okay.
everyone.
Bye
Goodbye.
bye. Bye bye, everyone.
Thank you. Bye bye.
Bye. 这李航已经把那个都已经放在 YouTube channel 上，已经直播出去了，是吧
Yes.
？OK，我觉得 Bruce
Okay.
的他的那个 presentation，他整个的那个语速啊，包括他的那个语言组织都很清晰。
Okay.
好，
That's good.
好嘞，你的那就行，那。